I'm going to go to one of those Lissajous curves because they're kind of interesting. I did this before. You do two trig functions like this that have frequencies that are not the exact same and are not simple integer multiples of each other, like cosine of t and 3t and sine of 5t, and graph these with parametric plot like this. You put them inside curly braces. T goes from, say, 0 to 2 pi. It gives you a pretty picture. Okay? It's called the Lissajous curve. In a physics class, if you got lasers going and mirrors that are shaking at slightly different frequencies, you can get pictures like this of the laser up on the screen. It's been done at Bethel here in this room before. What I want to do is I want to bring some other ideas in here. These are ideas I've talked about before to relate this ultimately to calculus and vectors. Will I test you on vectors? Probably not. But the conceptual ideas as far as especially speed and distance traveled and graphs, I could. R of t is going to be something called a position vector. Don't worry about what a vector is algebraically. Just realize that when I graph it, it's going to be represented as an arrow. Its derivative is going to be something called a velocity vector. And you can double check. There is the derivative. I differentiate each function here. F, the derivative of cos 3t, is negative 3 sine 3t. And g, the derivative of sine 5t, is 5 cosine 5t. You can also find an acceleration vector by differentiating that. But I think for the purposes of the short remaining time we have here today, let's just draw the parametric curve inside and manipulate and ultimately relate what we see to speed and distance traveled. Manipulate makes animations. I can put a parametric plot inside of it, and I'm plotting R of t from t going from 0 to some unspecified right endpoint b. Let's make it nice and bright blue here for the output. I'm also going to want to draw in some vectors here. You don't need to know this Mathematica code. I'm not going to test you on it. But what I'm trying to do is make a couple vectors that are reasonably easy to see. So I have to do some formatting commands here. Some arrows. The position vector starts at the origin and goes out to the point. And the velocity vector, it turns out, starts at the point and, well, goes out to the point plus the velocity vector here. B is going to be my animation parameter. It's the right endpoint of the interval. I also, to make the picture look nice, I think I need to do a nice plot range here. And also, it turns out to make the origin always stay where it should be. I need to do that. Okay, this should work to make a pretty nice animation here. Make the plot range a bit bigger. Actually, maybe I'm going to need to scale down the velocity vector. I'm going to divide it by 5 to make it smaller. How about 3? So there you see a blue arrow. That's the position vector. It's pointing to the location of the object as it moves. The red arrow is called the velocity vector. That's pointing in the direction of motion at any instant in time. Let's zoom in a bit closer. So imagine you're driving your car in a parking lot around like this, okay? Hopefully a cop doesn't come by and say, "What are you doing?" The blue arrow is keeping track of your position with respect to some given point. That would be, we're calling the origin here. The red arrow is keeping track of your velocity, not just how fast you're going, but the direction that you're going. It's always tangent to the curve. It's always pointing in the direction of motion at any instant in time. It's the direction you're facing, you can see. It gets longer in the straightaways when you're moving faster, and it's shorter in the curves when you're moving slower. The speed is the length of the velocity vector, called the norm. That's the speed. ABS stands for absolute value. You actually don't need the absolute value signs here because you're squaring the cosines and sine. I can say the speed is the square root of 25 cos 5t squared plus 9 sine 3t squared. That is the speed. It's not a constant speed. Make an ordinary plot of the speed from 0 to 2 pi. It's variable in kind of a wild way. You're speeding up, slowing down, speeding up, slowing down, speeding up, slowing down, speeding up, slowing down. But the principle still holds that the integral of the speed is the distance traveled. So I could try integrating this to find the distance traveled along that Lissajous curve. Unfortunately, I think there's no elementary antiderivative. Thinking. Come on, thinking. Will it go on thinking forever and not stop? It does give up at some point. I'm just forgetting how long it takes. Evidently longer than I was hoping. At some point, it's just going to give up and it's just going to say, give no output, essentially. Let me abort the evaluation. There's no elementary antiderivative of the speed function, but the integral still exists. The area under the curve still exists. We'd like to find it. We'd like to find the distance traveled along that Lissajous curve. What do you have to do? You have to do numerical integration. That's what. Meaning, by hand, maybe a left-hand sum, right-hand sum, average them, or maybe something more complicated. Now, this graph is complicated enough that that would be a big pain to do by hand and get an accurate answer. But in Mathematica, we can get an answer with something called n-integrate. N-integrate does numerical integration. It doesn't try to do the fundamental theorem of calculus. It doesn't try. When I was doing this, it was trying to integrate to find a formula for an antiderivative, effectively like using the fundamental theorem of calculus. Couldn't do it. Doesn't have an elementary antiderivative. But we can try to numerically integrate to find the area under this curve. What will it be? Can I guess? Well, certainly the answer has got to be less than 6 times 6, the area of this entire box, which is 36. Is it about half as much, like close to 18? I don't know. And why is my Mathematica stalling? This has been happening. I think I'm losing connection with the server. So it's a Wi-Fi problem. Okay. I think my Mathematica is not going to come out. Well, maybe. Did it work? Okay. Let's do this. I think we can get an answer. Here we go. Okay, bigger than 18, 24.6 would be the distance traveled. That's the approximate area under this curve. So the principles, the ideas, the concepts still hold. You just can't do the symbolic stuff. Could I graph the distance traveled as a function of t? Yes, but I won't take the time to show you how. It'd be a graph that goes up, but in a wobbly kind of way. Okay? Because you're speeding up and slowing down. Have a good day.